Hey, Thrasher here. This video, we are getting into the last major topic in our AP Physics 1 string of videos, angular momentum. Of course, we covered momentum earlier. As I've been saying over and over, this is the cousin of momentum, all right? So starting off, angular momentum. First, let's remember the original thing that we learned way back when, several sets of videos ago. Momentum is a property based on an object's inertia and its velocity. This is, of course, dealing with things that are translating, going from one location to another. The equation, P for momentum, is equal to M, that's for inertia, of course, and V for translational velocity. Well, we have a cousin. For angular momentum, it's the same idea. Regular momentum was based on inertia. Angular momentum is based on inertia. Regular or translational momentum was based on velocity. Angular or rotational momentum is based on velocity. But of course, we are going to deal with the cousin or the angular version of inertia, the angular or the rotational version of velocity. So for inertia, that's I. That mr squared kind of thing. That thing that can, change a little bit depending on the shape of the object, but it always says some version of mr squared. And what's angular velocity? That's lowercase Greek letter omega, this thing measured in radians per second. Now, L is the symbol used for angular momentum. I'm not sure why they use L, but they do. It's uppercase letter L, just as unintuitive as using lowercase p, I guess. So it's I times omega. The units, well, frankly, you're not usually going to be using the units. You're often not asked to calculate the angular momentum. Usually you do that for the point of this is to set up conservation of angular momentum, which we'll get to. But if you were asked, it does have units that don't have any special name. It's kilograms meters squared per second. If you're wondering where that unit is coming from, it actually has to do with the fact that angular velocity is regular old velocity divided by that distance. And what that means, or what that implies, is what's the unit for rotational inertia? Remember, it's always some form of mass times radius squared. There's that meter squared. And what are the units for angular or rotational velocity? Well, that must be m over s divided by, r. That'd be something in meters. So these meters cancel out. I still have a meter squared, and then I divide by a second. That's where that's actually coming from. Kilogram, meter squared, and then this would lead to a divide by s. Again, not really super important, but there is a basic equation for angular momentum based on the inertia of the object and its velocity. Okay, well, there is also impulse. We learned way back when, oh my goodness, that for a force acting on an object for a certain amount of time, there's a change in momentum. That's actually where our term momentum came from. Similarly, if I have an object that can rotate and I apply a torque on it for a certain amount of time, it's going to experience a change in angular momentum. Something else that is very important. There was a graph associated with the impulse equation. What we saw was that there was a force acting on something for a certain amount of time, and I'll keep it easy for right now. If I looked at this area under the curve, the area, that would be force times time, that would equal the change in momentum. So given a graph of force versus time, well, calculating the area would be valuable. It would give us the object's change in linear or translational momentum. The same thing is true. While these aren't quite as common as the first one, I drew that pretty terribly. All right, if I had a set of axes that was torque on the y-axis, so there's torque, and I had time on the x-axis, I don't know, maybe I have a graph that looks like this. Okay, so first there's a constant torque acting on a pulley or something, and then that increases. Well, if I could find the area under the curve, maybe doing the area of the rectangle, the area of this rectangle, the area of this triangle, that would be the change in angular momentum. So maybe, again, you might not be asked to actually straight up calculate angular momentum, but you might be asked, what's the change in the angular momentum? Well, okay, moving right along. For momentum, we saw that when there were no outside forces, no external interfering forces, the translational, or we called it the linear momentum of an object or even a system of objects was conserved. Here we go again, okay? For an object or system of objects, if there's no outside, no interfering torques, net torques technically, no interfering net torques, then the angular momentum of the object stays the same. conservation of angular momentum is very much a thing, and we can set up equations very similar to it, okay? Let's see how we go about doing that, and I'm going to do that with this classic scenario. This is the example problem for conservation of angular momentum. I have a figure skater. Sorry, I got this clip art, it seems like, from the 80s, but let's say I have this figure skater. Okay, so they're on the ice, so we don't have to worry about any friction or anything here. They're spinning around, they're going in a circle, they're doing a twirl, doing a spin, and then they tuck in their arms. They start with their arms outwards, and then they tuck them inwards. And if you've ever seen this on, I don't know, online videos, TV, movies, when they tuck their arms in, they are spinning faster. That's what I tried to diagram here. When their arms are further out, yeah, they're going at a certain angular speed, but man, when they tuck them in, they start spinning faster than they were before. Why is that? The proof is because of conservation of angular momentum. What does that mean? Their initial momentum is equal to their final momentum. Just like that. I'm going to switch colors, make it a little easier to see. Okay, what's their angular momentum? That's based on their rotational inertia multiplied by their initial velocity, multiplied by their angular inertia times their final velocity. Again, you could use I and F there, using I and F, initial and final in the diagram. We often, in my own physics class, use not to imply initial values and no subscript to imply final. Now, I don't frankly know what the rotational inertia is of a person. It's kind of complicated, but it's always some version of mr squared. Okay, times that omega naught. Maybe this is some initial value. The mass of the skater is not going to change. Times mr squared times the final value. Okay, well, what do we know is happening when you are tucking in your arms? Well, you're bringing your mass closer in. You are decreasing how far away that mass is distributed. So if I look right here, if this is R0 and this is R, the original value of R0, that's bigger. Well, that means, since certainly their mass isn't changing, that means that the rotational inertia of this figure skater before is larger than the rotational inertia of the figure skater after. By tucking in your arms, now your mass is closer to the center. You've decreased that rotational inertia. Oh, that in turn is key to understanding this problem. Because if I continue on, if I solve for this final velocity, okay, well, that's going to be that mr0 squared omega naught divided by, well, I'm going to divide this out, mr squared. And yeah, you know, a mass is going to cancel, okay, but what's that going to look like? Omega, the final velocity, is based on this ratio of their initial radius and their final radius. And if r is getting to be a smaller number, it's in the denominator. That means omega, the final velocity, must be getting larger. Oh, that's why the figure skater is speeding up. There's no outside torque, so their momentum is conserved. So by bringing their arms in, they are decreasing their rotational inertia. And therefore, by conservation of angular momentum, if you're decreasing that rotational inertia, even if you just focus on right here, if we are decreasing this value to keep this equal, this must be increasing. Technically, maybe I should have had like a I initial and an I final, but hopefully you get the idea. That explains why things speed up when you bring the mass inwards. There's a few other scenarios that have that same kind of explanation. Okay, the other example of conservation of momentum, that was for a single object. We also did conservation of momentum for collisions, and we're going to do that. It's maybe a little weird. In regular everyday life, you normally don't see two rotating things collide, but what I have right here is just that. Imagine I have a rotating disc that's attached to and can spin around a stick. Okay, and this one's kind of going downward, or the stick is upwards. This one is flipped. For this one, this bottom image, almost imagine spinning plates. You know, you have a plate and you spin it on a stick. Apparently people do that. I'm not sure why, but they do it. Now, again, we don't see this really in kind of regular everyday life, but if you drive a gas-powered car, there is something known as a clutch. When you change gears in a car, the clutch is used to change the gears. And the clutch, well, you know, it's a little more complicated looking. It's very much like this. You have one thing rotating, and then another thing comes together, and that combined rotation, that helps, yada, 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 change the gears of the car. So here's the scenario. This disc is rotating with a certain initial velocity. Oh, in fact, I'm sorry, it has a rotational velocity of 0 to start. The bottom disc, omega b, has some value. This bottom disc b is spinning. But then they come together. maybe my question is, how are these two disks going to be rotating? Are they going to be at rest? Will they be rotating in this direction? Maybe they'll be rotating in this direction. What's it going to be? How could I set that up? You could absolutely set this up with conservation of angular momentum. Because if this is my system, they're colliding, sure, but that's internal. So how would I set this up? In the beginning, these two objects are separate. So I have the initial momentum of A combined with the initial momentum of B. That must equal the final momentum, but now they are together. They're locked together. So just like when we had inelastic collisions, those two objects stuck together, it's the same thing. We can kind of treat it like one larger object. Okay, so that's going to be the the rotational inertia of object A times the initial angular velocity of object A, plus, inertia of B, and this is the initial velocity. Here's the rotational inertia, rotational velocity of B initial. That equals, we add them up, IA plus IB. Remember how we used to add the masses together in an inelastic collision? We would say, well, now they're kind of just like one object, so we can just add their masses up. That's what I'm doing right here. Now they're stuck together. It says that in the problem. If they're stuck together, they're like one bigger object, so treat their combined inertia just like one bigger object. That's why I'm adding them up. Times this final velocity. I'll put maybe omega prime. We've done that before. Okay, I know I kind of have to move this over a little bit, and I know I don't have any numbers, but we could solve for this omega prime. Let me delete my silly little plate diagram. So I'm still using this equation, but let's say I'm solving for this. All I'd have to do is divide this out. So that final velocity, that final angular velocity, oh my gosh, I know it's kind of an algebra mess, but it's not too tough. We just set up the same kind of conservation of momentum we did before, but now it's using the cousins, of course. Now it's using the angular quantities, all divided by IA plus IB. All right? And yeah, of course, if you were doing this with numbers, maybe you'd be simplifying things as you go, punching things into your calculator, but we can still use conservation of momentum for rotating collisions, and that's what this is. This is a collision. It's an angular kind of collision, rotating things, combining together, and we can still apply our classic conservation of momentum to solve for values, okay? As always, if you're in my own class, or of course, if you have a college professor, or you're using a textbook, or you have some sample problems in a book, you'll be getting practice. But that's it. That's angular momentum and its applications. We'll do one other application of angular momentum in the next video. All right? That's it. Thanks a lot for watching.